All righty. Welcome, everybody, to Lecture 12. We're almost essentially halfway through the class already, which is hard to believe. But so today we're going to pick up where we left off very briefly and then move into a new topic. But if you remember, on Tuesday we were talking about this notion of starvation and deadlock. And the important thing to note is that starvation is a situation where the thread waits for a very long time, possibly indefinitely. Deadlock is a situation that won't resolve itself. It's got some cyclic wait condition that basically is unresolvable. And so deadlock's a type of starvation, but not vice versa. Okay? Starvation can describe many things, including live locks, which are kind of unfortunate, continuous, inability to make progress. And we'll talk about a lot of starvations as we go on, especially, for instance, paging indefinitely. You can get into a thrashing situation, which is a type of starvation. So notice this cycle. This is our canonical deadlock cycle where a thread's waiting for a resource that's owned by another thread that's waiting for a resource that's owned by the first thread. That's a typical deadlock situation. All right? Any questions on that? We're good? So we talked about 4 requirements for deadlock. Now, these are necessary conditions. They're not sufficient. Okay? So what it says is the only way you can have deadlock is if you actually have mutual exclusion, where only one thread at a time can own a resource. Hold and wait, where a thread holding at least one resource is waiting to acquire an additional resource that's held by a different thread. No preemption, which means we can't just yank resources away, and essentially if we could yank resources away, we could resolve this deadlock cycle by just pulling one away, right? So, and then the last thing is some sort of circular wait, where there is a set of threads where thread 1's waiting for thread 2, is waiting for thread 3, thread n, back to thread 1. If you don't have all of these conditions, you're not going to have deadlock. Okay? Questions? And of course, we showed you a couple last time. We showed you at least one example where we had all of these conditions, but it wasn't quite deadlocked because there were more than one copy of a resource and the thing could resolve itself. Okay? So just because you have them doesn't mean you have deadlock. The other thing we talked about at the very end of the lecture was the banker's algorithm. And the banker's algorithm is a way of avoiding dynamically getting into deadlock. And so there's some key assumptions behind the banker's algorithm, one of which is that the thread pre-declares the maximum number of each type of resource it's going to want, okay? It doesn't have to ask for them all at once. So we talked about one option for this is everybody asks for everything at once and you don't get any deadlock cycles because you either get everything or you don't. This is a little more dynamic. It says, well, I'll declare what the maximum is, and now I can request and release and request and release as long as I'm never requesting more than I told up front is the max. Okay, so those are our assumptions. Is everybody clear on that? I just wanted to make sure. And then, yeah, question. Oh, good. That was a thumbs up. All right, and then this is simple use of the deadlock algorithm with sort of this suppose kind of aspect to it. So if a new request is coming in, you say, well, suppose I granted it. Let's see. Is the system in deadlock? Oops. Nope. You can't have it yet. You got to wait. Or, oh, it's not in deadlock. I'll grant it. Okay? And so this is a way of keeping the system in a safe state, which means that there's always a sequence, T1, T2, T3 through N, where you can complete thread 1, put its resources back, complete thread 2, put its resources back, till you get to thread N, and all the threads are done. So really, what the banker's algorithm is doing is with every request, it says, oh, if I grant that request, will I still have some ordering that gets me done? If the answer is no, you're in deadlock. Okay, and that resource will not be granted then until it would not take you out of a safe state. Question, yes? So what I mean is, let's suppose that we're talking about the operating system's granting these resources. The operating system knows, for all of the threads, it knows which resources it's already given. It knows what their maximums are. And so what happens is a new thread comes in and says, I would like X. And what the OS would do in running the banker's algorithm, it would say, well, let's suppose that we have X. So what it would do is it'd add X to that thread's set, and then it'd run the deadlock algorithm. It doesn't actually grant X until it runs it and makes sure it's not going to cause deadlock. Okay, so that's what I mean by pretend. It's like a thought experiment. All right? And the banker's algorithm prevents deadlocks involving threads and resources by stalling requests that would lead to deadlock. Note, it's important to note, so if you look at this, what the banker's algorithm does is it will prevent you from getting into these unresolvable cycles involving threads and resources. But it can't fix bad programmers. Okay, so if your thread goes into an infinite loop and holding resources that are needed to finish, that may be an unresolvable situation, but the banker's algorithm isn't going to fix that for you. So this is purely about resources. Okay? If the code is broken, or you don't do the right things, or you ask for more than the max that you said you would, any of these programming problems, and the banker's algorithm won't help you. Okay? All right. Good. And I actually, we had this example. Remember this one where we kind of started the lecture pretty much last time with this, where we said you asked for this was the bridge, right? You asked for X and then Y on one side and Y and then X on the other, and in very unfortunate circumstances, you get deadlock. Well, if you look at it, suppose thread A gets the first segment, and then thread B is about to try to acquire Y. Think what happens here. So if we pretend that thread B got Y, and now we try to run through, is there a way for the threads to get out? And at this point, there is there's no way for thread A to get what its max is, which its max is 1 of X and 1 of Y. Once we've granted thread A X and thread B tries to get Y, we would see very quickly that thread A could never complete, and furthermore, thread B could never complete because thread A's got X. And so that thought experiment of saying, what if we gave Y to B, now we run through it and we say, oh, we're deadlocked, and so what does it do? The banker's algorithm will cause thread B to go to sleep and wait without giving it the resource until this has resolved itself. And of course, in this simple example, what's got to happen is, A has got to give up X, which means it's got to acquire Y and then release Y and release X, at which point B will be woken up and it can go forward. Okay? So this is like the simplest example of the banker's algorithm you could come up with. All right? Questions? Because I'm going to move on to some new other topics here. So, all right. So then the other thing that's particularly appropriate for Project 2 is you're going to build a priority scheduler. And so then the question is, we talked about priority inversion. Can that cause deadlock? And of course we said, well, you got a priority scheduler. What's priority inversion? That's a low priority task somehow preventing a high priority task from running. Okay, so that's like against what a priority scheduler is supposed to give you. Okay? So, the question we might ask is priority inversion a type of deadlock? Okay, so what would be a type of deadlock? A type of deadlock would be an irreconcilable cycle that the only way to fix it is to take resources away or kill threads or something, right? And it turns out the interesting thing is, for all of its badness, priority inversion causes all sorts of very bad things. But one of the things that it isn't is it's not a deadlock, okay? And if you look through what's the easiest way for priority inversion to occur, it actually takes 3 threads in the following way. So the lowest priority thread, T1, grabs a lock. Okay, so you already know there's probably a problem here because a low priority thread has a lock. Okay, that's probably bad. Then the high priority thread, T3, tries to acquire it. So at the point where T3 tries to acquire the lock, what happens? We go to sleep with T3, right? Now, at that point, it's kind of a priority inversion, but it isn't quite, because what happens is T1 gets to run a little longer, release the lock, and then T3 can go on. So it is a priority inversion, but it's not really irreconcilable because T1 gets to run because T3 went to sleep, right? Now, it is technically priority inversion because T1 is running when T3 is not. So it is a priority inversion, but where this gets really bad is when T2, which is somewhere in the middle, starts running. Now we got a really big problem because T2 runs and, T2 runs, so T1 doesn't run. And so now we've got a problem because now we've got T2 is preventing T3 from running. That's a potentially long-lived problem, but it's not a deadlock. Why? It's a live lock because T2 could finish any time. And the moment T2 finishes, T1 runs for a little bit, releases the lock, T3 runs. Okay? So, everybody clear on that? So priority inversion is kind of any situation in which a low priority thread's preventing a high priority one from running. This idea of T1 grabbing the lock already gets you in trouble, but it's assuming T1's not broken, T3 will eventually get to run. Now, again, bad programmers unite, whatever. If T1 has the lock, T3 tries to get it, and then T1 goes into an infinite loop, we're also toast, right? So that's a bad situation. Now, here we go. Question. You're going to be, priority donation has probably already come up in section, but I want to ask myself or talk to you a little bit about as a remedy for this problem. So what is priority donation? Okay? That's when specifically high priority thread, we're going to call it TB, is about to sleep while waiting for a lock held by low priority thread TA. What happens? TB gives its priority to TA for a short period of time, just long enough for TA to run, release the lock. That's donation, okay? So A gets donated enough priority for B so that it runs at least at the level that B would have run. Okay, now if there was a C that was even higher priority, we don't get to run at C's priority because now we're inverting against C. But for this simple two-thread case, what happens, B is about to go to sleep. It says, well, who's got this lock? Oh, it's A. I'm going to give A my priority. A gets to run until it releases the lock. Then A goes down to being a lowly thread. And then B gets to run because now it gets the lock. Okay, so that's priority donation. Question? Yes? Well, what happens is as soon as TA releases the lock, TB, what does releasing the lock do? It basically takes whoever's a sleeper and puts it on the ready queue. So at that point, TB is at high priority on the ready queue, and it would be ready to run, and it does get to run as soon as TA says, oh, I released the lock, I'm going to lower my priority back down to where I was. Now TB is the high priority thing, gets to run. Okay? So, what's involved in this priority donation? Clearly the lock is now tracking ownership so that it can help with this priority donation thing. If you think back to all of what we've talked about with locks up till now, there really wasn't an owner. The lock was locked or it wasn't. And the owner was kind of implicit based on who's getting to run. Okay, and in fact, if you even look back at a few slides we had a little while back, I even said that. I have owner here, but I explicitly, this would have been lecture 7, I explicitly said, well, that owner thing is just for us because it's not a real thing. In priority donation, you really do need to keep track of who owns the lock in order to do this. Okay? Now, does this fix our problem? Yes. Why? Because, remember, T1 has the lock, T2 is running, T3 blocked. Briefly, what happens is because T3 goes to sleep, T1 gets raised to the priority of T3, and then it releases the lock, and then T3 gets to run. Does the priority donation take the lock away from T1? No. If we take a lock away, that's called preemption, and we know that's bad, right? Because that'll break whatever semantics you thought you were getting with the lock. All right? So, question, yes? So, Yes. So the question here was, is it possible to do malicious priority inversion by taking a lock and never giving it up? Yes. However, assuming that T1 has access to some lock, you as the designer have made an implicit statement that you're allowing T1 to do that. And so if it does screw up, it's on you. You've broken your own priority system. Okay? But if you think that T1 could be malicious, you're certainly not going to give it access to your own locks. Good question, though. Any other questions? Yes? Sure. This is deep philosophy. Who's preventing who from running, right? So T2 doesn't let T1 run, which doesn't let the lock run, or the high priority one run. So, but T2 preventing T1 from running, that's a normal priority thing. So the inversion is kind of the fact that T2 is ultimately preventing T3 from running transitively or something, however you want to look at that. So that's the inversion, is T2 is preventing T3 from running, not that T2 is preventing T1 from running, because that's okay. That's a priority, normal priority situation. Did I convince your philosophy to go forward? Yes. Okay. Good. All righty. So we are going to we've been kind of talking about some pretty low-level stuff, a bunch of OS concepts, some concurrency. In the spiral of topics, we're going to talk about address spaces, and we're going to talk about memory mapping and paging and so on. And the thing about this is that basically we're going to talk about address translation, and that's going to be an enabler of all sorts of important things. Protection, secure multi-programming, isolation, memory resource management, I/O efficiency, sharing, you name it. This is kind of involved in it. So this is a big topic for you guys, kind of important. Pushing particularly on translation. And if you remember, first lecture or two, we talked about 4 fundamental concepts, second lecture. One was the thread was an execution context. It's a sort of a program state with program counter registers, etc. We had the address space in there, if you remember, either with or without translation, where the address space was a set of memory addresses that are accessible to the program. And it may be distinct from the physical machine. Okay, so in fact, it's going to be distinct once we start translating. The third thing was kind of the process, which was a thread plus an address space. The fourth thing was dual mode operation, which basically says the system has a kernel and a user mode that's separate. Now, we had there was a true-false question on the exam, and we had some folks that kind of missed this. So the dual mode is essential to protecting the address spaces. That's true. The reason is that you can't allow a user to alter their own address space. So you have to say only the kernel can change the page table, and therefore if you don't have a dual mode system, and you don't have compiling, and you can get around it. But by and large, if you don't have a dual mode system, you can't do protection. Okay? We're going to bring that back into the picture here and remind you guys of this. Okay? So, let's start something simple here. So, you guys all took 61C. You remember bits and representations and 2's complement and all that stuff, right? It's right at the top of your brains. But let me remind you a couple of things. So what is an address? So an address may be k bits long, so it's a set of 1s and 0s. What does that mean? That means that the address space is a set of 2 to the k things. So if you've got 8 bits, 2 to the k is 256, you only got 256 things. Okay, that's a pretty boring address space. We're dealing with 32 bits or 64 bits, so it gets a little bigger. Okay? And what's a thing? A thing is a byte, which is 8 bits. Okay, now these are things that I assume you guys learned in freshman year, let's say, but maybe if you didn't, we're going to make sure you remind them. So a byte is 8 bits. And when you talk in a modern processor, you talk about what's the size of memory. You're talking about bytes. Okay, in the old days, there were even 6-bit items that were units, but pretty much today it's all bytes. And so you might say, well, what's 2 to the 10th bytes? Okay, where a byte's abbreviated. So there are a lot of things that you guys ought to just memorize and have totally figured out. Like, for instance, 2 to the 10th is 1,024. A byte is a capital B, and so we call that 1 kilobyte. Okay? And notice for memory, I'm going to say this later, 1K is 1,024. It's not 1,000. Okay, so a KB, capital K, capital B, is 1,024. How many bits to address each byte of a 4 kilobyte page? How would we figure that out? Yeah. Good. Or you could take log 2 of 4K. Yep, I like that. Or you could say, well, 4 kilobytes is really 4 times 1 kilobyte, which is 4 times 2 to the 10th, which is 2 to the 12th, which is 12 bits. Now, okay, so 12 is the log base 2 of 4, right, 4K, okay? These are all things you know, right? Like you add exponents, so 4 is 2 to the second, so 2 plus 10 is 12. Yes, you guys all know this. How much memory can be addressed with 20 bits? About a megabyte, right? 32 bits, about 4 gigabytes. 64 bits, a lot. Okay, 1.5 exabytes. That one I don't usually expect you guys know. 20 bits, 10 bits, those are things you should know. Okay? Questions? Okay? 61C, right? So, if you remember, back when we were talking about address spaces, we sort of said, well, what's the address space that a processor sees on a 32-bit processor? Well, 2 to the 32nd is about 4 billion, which means that if you were to lay the address space out, you start at 0 on one side and all F's on the other, and you get basically 4 billion bytes. Okay? How many people are comfortable translating between hex characters back and forth? Okay, not so many of you. You might want to practice a little. These are things that, you learn once and then you never forget. It's like riding a bicycle until you hit the wall, right? So, an F is 4 ones and a 0 is 4 zeros. And between that, 9 is 1001. I mean, these are things that you just memorize the 16 entries and you're good. But how many 32-bit numbers, so those are integers, fit in this space? Well, because these are bytes, you need 4 of them to get an integer that's 32 bits, right? So 32 bits is 4 bytes. So 2 to the 32nd over 4 is 2 to the 30th, which is about 1 billion integers fit in there. Okay, now I realize, just don't worry for those of you that are totally blurring over because you know this so well, I'll be done in a second. But I would get to where you're comfortable doing divisions like this, okay? So the fact that we're normally talk bytes means that when we talk about things bigger than bytes, you're dividing stuff, right? So 2 to the 32nd over 4 means that every 4 of these is an integer, a 32-bit integer. Okay? Good. So, and then when we talked about address spaces, we kind of said, well, what happens when the processor reads or writes to an address? Well, it might act like memory, but it might cause an I.O. operation. We'll talk about memory mapping. It might cause the program to abort, segfault. It might communicate with another program. There might be lots of things that happen when you do a simple read or write. And what we're talking about today is the beginnings of how that works. Okay, so how do you make it cause an I.O. operation? Well, certain ranges of addresses actually go off the bus and go out to I.O. Or how do you make it abort? Well, you mark certain parts of the page table as, read-only, and when you write to it, it aborts. So we're going to start talking about page tables here, okay? So, and then finally, the typical structure of the address space, and this is inverted, so that 0's at the top here, but you got a code segment, you got data, and then the heap grows up towards FFFF, and the stack grows down towards 0. I inverted that just to see if you're awake, okay? And then typically the program counter points somewhere in the code segment, and the stack pointer points somewhere in the stack. Good? All right. So, this project 2, you're going to start looking at the heap. So what happens when malloc runs out of memory in the user's address space because you start talking to a hole with no physical memory? There's going to be a system called sbreak that actually helps ask the kernel for some more pages so that malloc, which is running at user mode, gets to run. So this is something you get to play with now, okay? All right. So let's move forward. And 61C end, right? Okay, so physical reality is that different processes and threads all share the same hardware. So we've been talking about multiple processes and multiple threads, and you need to multiplex the CPU, you got to multiplex memory, you got to multiplex disks and devices. And why worry, for instance, about memory sharing? Okay, so you've got these memory chips, and you chop it up into little pieces and give it to each of the processors. The question is, why does this matter? And the thing that matters here is the complete working state of a process is in memory. Okay, and so the memory is the fundamental piece of this, right? There's a few registers, but mostly everything's in memory. There was that question on the midterm about what do you need to save and restore on a context switch. It's already in memory. You don't have to save and restore it because it's already in memory. Okay, so we're probably talking about like register state or stack pointers. Okay, so memory is important. And consequently, you can't just let different threads use the same memory. Okay, so if you've got some vital secrets or vital part of the process state in a part of physical memory and you let another process touch it, you're going to get bad results. So that's getting into this translation and protection. This is kind of like a physics thing back to philosophy, right? Two different pieces of data can't occupy the same bits in memory, okay? And you probably don't want to have different threads from different users or processes even have access to the same data. So if you remember, we had this picture, right? This was highlighting that the threads, there can be many or few in the process. They encapsulate the concurrency portion. The address space is the protection domain. And so address space typically has code and data and files and registers and stack. Okay? And so how do we approach this? So, just to remind you one other thing, we had this idea that the processor might actually be working with a virtual address space. The processor is using addresses, but there's some translation thing in the middle so that memory, the physical memory addresses may not have anything to do with the processor's addresses. Okay, and I'm going to pause on this just long enough to ask if there are any questions on that, because that's really the topic of today. Okay, are we good? So processor, reading and writing, program counters, stack pointers, memory reads, produce addresses that get translated into physical ones, and that's where things are actually in memory. And that may scramble. Okay, there may be no relationship between what the processor thinks is a linear order and what's actually in memory. Okay, and that's kind of the power with this is, can we translate in a way that gives us the type of protection we care about? Okay, without being too expensive to do in hardware. Because any of you who have taken 152 or 252, you got to be careful about hardware, because when you're talking about physical things, they're expensive, they're slow if you put too much of them together. Okay, so an arbitrary translator that calls an oracle and computes the 23rd digit of pi before it does the translation probably is going to be a lot of hardware, and it's not going to be fast. Okay, so there are several things we get out of multiplexing memory between multiple processes. So one is, if we're careful about the way we multiplex, we can get protection. So remember, the simplest idea there is process A, process B, process A, process B. The physical parts that A and B touch are totally not related to each other. If we do that, we've got protection, right? Because A can't even address the notion of something that B has got. Okay? And so that sounds good. Controlled overlap, though, is useful. Okay? We want to separate the threads. The separate state of the threads shouldn't collide unless we're actually communicating with that. So good examples, as I'll show you later, are kernel and user have ways of communicating. Two processes may set up shared pages and want to communicate. So we want to control the overlap, not allow arbitrary overlap. And then finally, translation is really the ability to translate accesses from one address space to the other, where the way we think of this here is we think of the virtual address space and the physical address space one's translated into the other, and they're separate from each other, okay? And the side effect is kind of translation's king, which is why I talked about it last, because basically you can use translation to avoid overlap. You can use it to give a uniform view of memory so that every process thinks it's got 0 even when it doesn't. So there's a lot of powerful things behind translation, okay? The trick is how does it actually work? Okay, so midterm 1, we'll talk about that in a second. Were there any questions on these 3 things here? Forgot to ask. Good. So midterm 1, we have regrade requests up until Monday. There's solutions on the resources page, and Piazza has a pointer to it if you're looking. Also do our peer evaluations for Project 1. So these are required. I had a couple of folks ask me, do you get points for it? Think of this as a way to avoid having no points. All right. You get 20 points per partner. So if you have 3 other partners, because there's a 4-person group, 3 times 20 is 60, in case you weren't aware of that. This is in keeping with earlier slides, right? And you give those to your partners any way you want. So one question that was on Piazza is, can I give more than 20? Yes, you could give more than 20 if you end up giving less than 20 to somebody else. It adds up to your number, okay? Don't give yourself points, okay? All right, and Project 2 has finally been released. I apologize for the fact that that wasn't out yesterday like we said. There's going to be a scheduling lab where you get to play with schedulers a little bit that will be released next week, which we'll also put up. But all right, any administrivia questions? Yes? No, it's part of Project 2. It's just we want you to get going on Project 2 first. And so, but it's you'll see it smack in the topic of Project 2. It's just that we're not going to release it quite yet. Think of it as like 2B or something. Not to be. That's the question. Any other questions? Okay. So, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, right? So, if you remember, we talked about loading, where part of the loading process to go from this green thing here, which is a program you've written, to a binary on storage, to a process running in memory, there's several different aspects of that, right? You got to compile it, then you got to link it, then it gets loaded into memory. So that compile, link, load has a lot of interesting aspects to it. Like, for instance, going from disk to memory might involve on-the-fly linking with shared libraries, dynamic libraries, as you load it into memory, so that there's only one copy of that thing that does ECC encryption, but all the processes that are running all have a link to that single library that's in memory somewhere. That linking happens dynamically as part of the loading and execution process, okay? So let's start this process very simply. So here is a MIPS or a MIPS-like instruction set. The details here are not too important, except that this little chunk here is a storage for memory that you're going to use. So that's an array in memory. This is a load word, and this is a jump and link like a call. And so when you assemble it and then link it, what you see here is these are assembly language, machine language versions of the thing at the left here. But what's interesting here is if you look, this load word says, I want to load from 0 offset from this array in memory. And so how does that look in binary? What that looks like is this instruction, 8C20, which is the load word, has to be supplemented with something that points at the memory where the array is. And that's why I've got it in red. Okay? And that's part of what the compiler and linker does. Fortunately, you don't have to do that by hand because it's a painful process. But I wanted you to notice, for instance, the fact that we're loading a word, which is a 32-bit thing. Remember what we said earlier? If you're loading a 32-bit item, how many bytes is it? It's 4. So that means that to specify an address, in fact, I don't need as many bits as I would. Remember, instead of 32 bits, I only need 30 bits, for instance, or instead of 16 bits, I only need 14. So in fact, what happens here is this 0C0 that I put in this offset is actually representing an address that's a little bigger, that's 4 times the size because I'm loading words. Okay, so that's part of getting very good at thinking in terms of, I'm loading integers, therefore some of the bits are low. And I wanted to show you this, for instance, 0C0, here we go, here's your practice for hex, right? So 0 is easy, 000, C1100, that's easy. Some of these are easy to remember. 1100 and 0011 is 3, so those are good ones to remember. And then all zeros again. That is an address to an integer. When I multiply by 4, it's an address to a byte. That's the beginning of where the integers are stored in memory. Okay, so this, I realize this representation thing that you had in 61C that you've all conveniently or whatever forgotten is something you need to pull out of the depths of your brain. Okay, and that's why this first lecture I'm just giving you some of these things. One thing that's very useful to remember is notice when I take this 0C0 and multiply by 4, what happened with the bytes or the bits down here? Anybody see what went from here to here? What's different? What does multiply by 4 do? Shift left by 2 bits, right? Good. Okay, multiply by 2 is shift left by 1 bit. Okay, these are all things to remember. You guys, I'm sure, got that from 61C. So once we've linked this, which is basically fill in all of the unknown addresses and so on, then we can load it into memory somewhere. And notice that this is loaded at starting address 0300. Why? Because that's what we linked this for. We linked this for something where data 1, which is the beginning of it all, was address 0300. And so these instructions that are in memory there are customized to only run properly at 0300 that address. So when the program counter of the processor is working its way through, it's working its way through these values that are going to map only properly if this thing has been loaded at 0300 hex. Okay, if I push those bytes and I load them somewhere else and I start trying to run it with the program counter with it somewhere else, it won't work properly because the addresses weren't linked for anything other than 0300. I'll pause for that for a second, okay? Because that may not be something you thought about in 61C too much. But what I'm assuming here for a moment, how many people can see, is there translation assumed in what we're talking about here? There's not translation at the physical level because we're loading directly into address 0300 here, right? So this is a case where the translation box is null and void. It's just passing addresses straight through. But let me show you, for instance, suppose we want to run the same application and we want 2 of them in this untranslated memory space. What we have to do is, in fact, translate the addresses to some other place. Like here, I'm running it at 1300. And if you were to examine all of the bits representing that program, they're different because the thing has been compiled and linked to run at 1300 hex. So those 2 programs, as they appear physically in the memory when I'm running them at the same place or at the same time in different places, are different. The bits are different. Okay? I'm pausing just to make, because this, I'm sure you haven't thought this through, but I just wanted to show you. This, by the way, is why translation is so powerful if we can even give everybody the notion they have 0 of their own. Because if every process gets to have 0, then we get to translate virtual addresses so that we can make it look like every process has its code running at 0300. They all have 0300, but it translates to different physical parts of memory. That's going to be a very powerful thing. But for now, we're assuming something not very powerful, which is we basically have to translate physically for every place we want to put it in memory. Welcome to MS-DOS, okay, or Windows 3.1, or the original Macintosh. Okay? And where does this translation take place? Well, it could be in many places, at compile time, link or load time, or execution time if we have something else going on like translation, okay? Now, this process of going from a program to a binary image that's running in memory goes through many steps. So you write your program, you compile it, you get an object module, you link it with your other object modules with a linker, it gives you a load module, and then when you run it, the loader links it with system libraries, and that potentially produces an A.out, which is now very runnable. And then when you load it to actually run, you might get dynamically linked libraries linked in there. So this whole process of going from your C code to something that's actually being run by the processor is pretty complicated, okay? And so addresses can be bound anywhere along this path. So one way to look at what this process is doing is it's taking and binding, where is data 1? Well, data 1 in this case is bound to 1300. That process had to happen at a linking stage here, okay? But that can happen at many places along the path, and this depends on whether we have, for instance, hardware support for translation or not. It also depends on the operating system, okay? And so one thing I did want to point out for those of you that, I said it already, but dynamic libraries are an amazing innovation, okay? So what they are is it's the ability to have libraries that are loaded into a part of memory and shared by a whole bunch of executables simultaneously. And what happens is when you build the code, it actually puts little stubs in so that when you try to call the encryption function, it goes and it triggers a linking process which goes and links to the dynamic library that's sitting in your address space, and you get to use code that everybody else is also using dynamically. Okay? And so, yeah, when you have a very complicated library and you link it in many programs and you run them all simultaneously, there's only one copy of each binary actually running, which is kind of a nice savings in total space. Okay? Good. Questions? Now, so if we go back to the beginning of time, okay, I don't know, there's a bunch of lava and no dinosaurs yet, so that's a little too far back. So if we go back to the beginning of computing, we had unit programming, all right, which is applications always run at the same place in physical space. There's only one application at a time, and applications can access any physical address. This is kind of your address space looks like this, and the application is given the illusion it's got a dedicated machine because the application has a dedicated machine, so it's not even an illusion. Okay, so this is sort of prior to operating systems. All right, this is not particularly interesting. Now when we start getting primitive multi-programming and we don't have any translation or protection, now we've got Windows 3.1 or MS-DOS. Here we have to prevent overlap automatically by the loader, but not the hardware. And so here is that example I showed you where application 1 is running, say, at 0 and 2 is running at 20,000 hex. And we have to relink the code to run in different places in order to make it work properly. And that's the only way we can have more than one thing running at once. Okay, and that was messy. Okay, I'll tell you that was very messy. Okay, because the process of starting a binary would have to do linking to make this work properly. All right. No protection. Anybody can write anywhere. Very common applications write to the operating system. Change it any way they want. Okay? Just the name of the game. And actually, people exploited that. Yeah. Yep. The heap is not handled well. And applications don't play well with each other. So the advantage of this, of course, is very common in an MS-DOS or Windows 3.1 application. You'd have these things you'd run at boot time, and their job would be to install themselves into the operating system and link themselves in. So you could get new functional modules to do a better job of printing. You could get what were called TSRs, which were those are terminate and stay resident programs that would make that every time you pressed escape, it popped up something on the screen or whatever. They were fundamentally ability to change your operating system and programs on the fly. I guess that's cool. You know, all of us wrote them and, you know, passed them around to people. But of course, this is very bad when there are bugs, and it's even worse when there's malicious programs. So you can imagine we evolved past this pretty quickly, right? So how do we protect? Well, you already remember we started talking about this, lecture 3 or something, which was this idea of a base and limit of some sort, right? So if we have no translation, but we have a base and a limit register, then we can say, well, application 2 has to be automatically relinked to run at 20,000 hex, but we can prevent it from getting outside of its little cage, and therefore it can't mess with the operating system. Everybody remember this? It's ringing a bell a little bit, right? So you have 2 special registers, base adder and limit adder, and you cause an error if the user tries to access an illegal address. An assumption here is somehow that the operating system is running in dual mode such that only the operating system can change the limit address or base address. Why? Why is dual mode desirable here? Yes? Yeah, otherwise there's no point, right? What's the point? Okay, so that's why dual mode is so important. It's because once you put a cage around the application, you got to make sure the application can't just change the cage and get out. Okay, that would sort of defeat the purpose. And so when the operating system is running switch or multiplexing things, what it does is it loads and it stores out the old limit base and loads the new limit base. And as a result, when you switch, basically you get to go from application to application. Okay, so this is very primitive, but it still has no translation. So if you remember, we went past that by starting to put in some translation. And I wanted to give you a couple of terms here just so you know what we're talking about. So typically, this translator here is called a memory management unit, MMU. And what happens is the CPU's addresses go through this MMU to produce physical addresses. And typical systems actually have a translated and an untranslated view. Who gets to use the untranslated view? Yeah, only the OS gets the untranslated view. All right. Some processors provide that untranslated read or write, which is nice and simple, although it makes virtualizing harder sometimes. So this is less desirable these days. But this translation box of the memory management unit basically converts from virtual addresses to physical addresses. And translation makes it easier to implement protection, because if task A can't even gain access to task B's data, then there's no way for it to screw up. But it also really makes linking easier, because now we can make sure that every process gets 0. You get your own chunk of 0, and now you can link the program the same way no matter how many copies of it are running, because all of them's got 0. And how do they all have 0? Well, they all have 0 because that every one of them points to a different part of the address space. Okay? And in fact, in the case of shared libraries, they could all point to the same part of the address space. So the arbitrary translation starts becoming interesting here. Questions? So MMU, that's your acronym of the night. Okay, Memory Management Unit. All right. Now, if you remember, we talked about base and bound. Well, that actually was from a real, very cool supercomputer called the Cray 1. It looked like this. Okay, it was circular, and it actually had bench around here that kind of covered the cooling. Anybody want to guess why it was circular? Electromagnets? No, it was all about making it easier to keep wires short. So Seymour Cray, who made the Cray 1, was an amazingly brilliant crazy man who basically, he would go in and he'd measure every wire so that he knew exactly what the speed of light time was from the beginning, from it entering the wire and getting out of the wire, and that was how he made this the fastest machine on the earth at the time. Okay, so every wire was measured down to the millimeters, and it was cooled to keep everything running as fast as possible. But anyway, part of that architecture was base and bound, and that's this very simple translation where every virtual address, we add the base to it, and then we have a bound where we check it. And this is fundamentally different from what we showed you earlier because, as a result, every application has its notion of 0. What happens is you add its base to it, and that goes to a different part of DRAM. So everybody gets to think they have 0, but it goes to a different physical spot. Okay? And so you're using base and bounds for dynamic address translation. So translation's actually happening during execution, and we're altering the address. Okay? And we're generating an error here if they try to go outside of their space. And it gives the program the illusion it's running on its own dedicated machine with memory starting at 0. Okay. Does this ring a bell? It was like lecture 5, 6, somewhere in there. I know that's going way back, a month ago. Okay, questions? I didn't talk about the Cray 1 back then, but it's a very cool machine for its day. Okay, so what's wrong with this basic concept of base and bound? So we're now going past where we were, which is, suppose we've got base and bounds, and notice this is a part of the physical address space, and notice how I have the OS in one place, and then I've got 3 processes that are running. Everybody with me? Okay, you just look at that, it says processes 2, 5, and 6. And what happens when process 2 finishes? Well, it leaves a hole. Okay, but then maybe we start up process 9. Okay, and then we start up process 10. And 5 ends. But process 11 doesn't fit. So now we got to start copying things and moving them around in order to find space for 11. Okay? So this is not great over time. Okay? And the biggest problem here, if you were to analyze what's going on, is that processes are not all the same size. They're different sizes, and that leads to, what's the word I'm looking for here? Fragmentation, right? So the problem is this technique doesn't give us, it doesn't deal well with fragmentation because the fragmentation is here's a hole and here's a hole, and they need to be combined to get us process 11. But we also don't deal with sparse address spaces either. So if you look at what we've got here. Sorry, process 2 may want to have a stack and a heap. Well, in order to have a stack and a heap, I have to pre-allocate all the space in there with physical DRAM in order to have a stack and a heap. Okay, so there's no ability to just have holes in the address space for future use. I have to actually come up with physical memory, right, which is pretty bad, right? And it's really hard to do interprocess sharing because by its nature we have confined processes to a little region of memory. And so if they want to share with some other process, they can't. Directly, they got to go somehow through the operating system. Maybe they do a system call, and then the operating system forwards it up to the other guy, but it's messy. Okay, so there's no direct memory sharing here either. All right? So, why don't we take a brief break, and we'll come back, and we'll make this more flexible. Oh. One of the big problems that we talked about with this support here is the inability to deal with a sparse address space, which is we'd like to have holes so that we can have the stack grow and the heap grow without having to pre-allocate a bunch of memory. And so we can go to something more flexible, which is instead of having one basin bound, we can have many. Okay, and so that's called segmentation. And if you look at the logical view of the program, you typically have a bunch of segments, which are things like stacks and symbol tables and what have you, code. But then when it's linked to the actual application, this becomes regions of contiguous memory. So like 1 might be the code, 4 might be the stack, 2 might be the heap, and 3 might be something else, okay, a shared region, whatever. And so by having multiple basin bounds, now I can place them in memory in ways that let me grow. Okay, so for instance, by putting 4 in, so this is sort of the virtual view of 4, and by putting the physical view of 4 in memory, say in this way, then I can allow 4 to grow down, and if I ever exceed my space, then I might get a segmentation fault. That's where that word comes from, and I could add some more memory to that segment. Okay? Now, let's take a look at how we might do that. And so what we're going to do is we're going to start talking about translation in a big way here now, okay? So let's say that these green registers, I've got 8 of them just for example, are in the processor, and each of them represent a base limit pair, okay, just like basin bound. And so the segment map here is going to be inside the processor typically. And what do we do when we translate the processor's address? Well, if we have more than one segment, then we need to come up with some way of saying which segment. Now, what I'm going to do first for you, and in several of these following slides, is I'm going to take this address, which is 32 bits. Okay, remember we did all that at the beginning of the lecture. And I'm going to take a couple of bits off the top to tell me which segment. Now, can somebody tell me how many bits are at the top here in red? Of my 32 bits, how many bits? Okay, quick. Said 3. Yep, 3. Why? Because there are 8 combinations. What's 2 to the 3? 8. So if I take the top 3 bits, right? The top 3 bits will tell me which of the segments do I want, and the offset is the rest of the address. Okay? And so how do I translate? Well, I take the top 3 bits. If the top 3 bits are 0, 1, 0, that would be the number 2. You guys are all going to get really good at this, right? The number 2 points at this register 2. I find out what the base is. I add the offset to it. That gives me a physical address. And I take the limit and check my offset. And if it's too big, I get an error. So this is a multi-segment version of basin bound, where what I'm doing is I'm taking a part of the address to indicate which segment I want. And there's as many chunks of physical memory as there are entries. So I can have up to 8. But notice something interesting here. I was going to say that in a moment. I'll say it in a moment, but I'm going to say it here now. Notice these V's and N's. What do you think they stand for? Valid and not. Okay, valid. So if I try to access one of these guys that has an N, then I get a segmentation fault as well. So I don't have to have as many segments as I have table entries. I can have less. Okay? Now, however, I do also want to point out this thing with the red is a little unusual for segments, because what usually happens on a processor like the x86, like what you guys are using, is which segment I'm using actually comes out of the instruction bits. So for instance, if I look at a move ES:BX, AX, you guys are all seeing something that looks sort of like that, right? That ES specifies which segment register I want. Okay, it's the execution or the E segment, and that will basically look up in a table, the segment table inside the processor, to get the base and limit. Okay? So, two alternatives I've shown you already. One is you could take some bits and use that to pick the segment register. The other is you could have some bits in the instruction itself. Okay? And so in the x86, they don't have bits in the virtual address. They have them here, but there are other processors that do it this way. The other thing is, of course, I told you about the v and the n, and we can get an access error if we don't have valid. So we have two possibilities for error. One, my offset's too big for the chunk of memory I've given. The other is that there's an access error because it's an invalid chunk. Okay? Everybody with me? So what do I mean by this? This is coming out of the processor. I go through this translation process, and when I'm done, the physical address is the thing that goes to the DRAM. So this thing in the middle is a translation box. Or that could be a very simplistic MMU. Okay. And the other thing is, where are these green things? These are in the processor. So you could ask the question, what do you save and restore on a context switch? The green things, because they're in the processor. Okay? All right. Now, if you look at the Intel x86 spec, for instance, the 8386, in fact, there are a whole bunch of segment registers. There are at least 6 of them that are preloaded, CS, SS, ES. So the CS is the code segment, SS stack segment, and then there's some other ones that are commonly used. And those are actually in the instruction, and they sort of say which of the preloaded segments do I want to actually use. So that's part of the x86 spec. And that's why when you look and you do disassembly in GDB, you actually see segment specs with colons. Okay? Because they're talking about which segment register. Now, I want to show another example. So here we're going to make this explicit. You guys get to manipulate bits today. All right? Isn't this fun? So, I know a night you get to manipulate bits is always a good night, right? So, suppose we've got a 16-bit processor, because otherwise this would be really messy. All right? And that 16-bit processor has 16-bit addresses. So the virtual address is up here, 16 bits. How much memory can I address? How many bytes with a 16-bit processor? Yes? Yep, 64 kilobytes, which is how many actual bytes? 65,536, right? So you should know your power is 2. So anyway, but let's take a look here. So here's my virtual address. I've only got 4 segments, so I'm only stealing 2 bits at the top. All right? So here's my virtual address space. Do you see how it's sparse? Why is it sparse? Because if I start with 00 up top, that's going to be everything from 0000 hex to 4000 hex. Why? Because what's 4? 4 is 0010, so the top 2 bits are 0. Okay? The second part of the virtual address space will be everything from 4 to 8, or 4 to 7 FFFF, and then from 8 to B FFFF, and then from C to FFFF. And so if I want to look at what happens if the processor addresses something in that pink region, well, let's take a look. We know it's segment 0 because the top 2 bits are 0. And I go up here, where's segment 0? Segment 0 has a base of 4,000 hex and a limit of 800 hex. And so notice that means that anything within this part of the virtual address space gets translated to this part of the physical address space. Why? Again, I take any address in here, I strip off the top 2 bits, which I know are 0, because I'm in this region here. That goes over to the table. I find the base is 4,000, the limit's 800, and that's a range of addresses from 4,000 to 4,800. So anything in here goes there. If I try to address something in the blank region, what will happen is I'll violate the limit and I'll get a segmentation fault. Okay? And now we could similarly look at this. So, for instance, now that I have a bunch of different segments, this purple thing, magenta, could be a shared segment between 2 different processes just by setting their different segment tables up to share. Okay, so suddenly I got a lot of power to have stack segments and heaps and shared segments and what have you. Okay? This guy, segment ID equal 1. I know if I look up 1, I see that the base is 4800, and from 4800 to 5C00, because I have 4800 as a base and the limit's 1400. Ooh, you guys get to start figuring out how to add in hex. That's fun, right? But, questions? Okay, you're starting to get it in principle, right? But maybe a really explicit example could be useful. All right? So, let's translate. Here's some code. Here's a segment table, a little different from the previous slide, but that's all right. Let's suppose that we're going to start with the PC is at 240 hex. So the PC's right there. See that? I highlighted it. So what does that mean? That means the program count register in the processor is 0000240 hex. Now, in the processor, so the processor that's running a process thinks it's running at 2400 hex. Let's figure out where that actually is in physical DRAM memory. Everybody understand what we're trying to go after? It's different, okay, because that's a virtual address. So first, the processor fetches 240 hex virtual address. So what does it do? The MMU says, what's 240? Oh, that's 0000, and then 0010, and then 0100, and 000. Believe me, that's 0 is 000, 2 is 0010, 4 is 0100, and 0 is 000, okay? And if you look, what are the top 2 bits? Zeros. What code? It's the code segment. Well, that's good because I'm fetching from it, right? So it's virtual segment 0. The offset is everything left over after I take the top 2 bits off, and that's going to be 240 is the offset. So my segment is 0, the offset's 240. And so what happens is, how do I do my base and bound? I look it up. I say the base is 4000. And so I take the 4000 base, and I add the offset, and I get 4240 hex. So in physical DRAM, based on that translation I just did, the processor asking for 240 hex actually goes to 4240 hex in the DRAM. Now, question, did I violate the size of this segment? Well, 240 hex is smaller than 800 hex, so the answer is no. Okay, so I'm operating in the code segment. You guys are just like rapt, right? This is so fun. You guys are just, oh, this is going to be great. I can't wait to tell my friends about this. So when I fetched that instruction, what happened was it went through the MMU, then the DRAM was told to get 4240. It came back with the value of the instruction LA $A0, okay? So it's loading an address for wherever var x is, which is down there into register A0. So it better be the case that when I went to fetch, I got back the instruction I thought was there. What does that mean? I properly loaded the code at 4000 hex into physical DRAM. So the operating system did the right job. All right? And so now what I'm going to do to execute this load address instruction is I'm going to move the address here, 4050, into A0. Okay? That's what this load address instruction does. Don't worry about which assembly language that is. It's fine. Let me ask you this. What do I load into A0? Do I load 4050 hex, or do I try to translate 4050 hex? No. Because the processor is working 100% virtual, right? The processor doesn't have any idea that there's translation going on. So when it loads, it thinks that 4050 is where var x is. 4050 is a virtual address. That virtual address gets loaded into A0 because the processor's working in virtual space. It doesn't know anything about the DRAM. Okay, so that was a good question, right? Do you see that? When I ask for what is the address where var x is, it's the address, the virtual address is 4050 hex. Okay, so you see why this is a good thing to go through. And by the way, we add 4 to the PC to go on to the next one because instructions in this RISC processor are 32 bits long, and so we have to go 4 bytes at a time with the program counter. Woo! All right, so now we're on the next one. Boy, we're really passing along here, right? So now we're going to do a jump and link. That's a call instruction to the string length procedure. And notice that we're going to fetch from 244, and it shouldn't surprise you that when we're done, we end up with 4244 hex, because look, when we got the first one, it was 4240. The fact that we get 4244 binary, in physical DRAM shouldn't surprise anybody, because it's just 4 later in physical memory, okay? And then we're going to move, we're going to go into the string length. So we're going to move 248, which is the thing right after this, into the return address, because when we return, we're going to come back to the instruction after the jump and link call, right? So, why do we move 248 into the return address and not a translated 248? Because the processor's working on virtual addresses. Okay? And why do we move 360 into the PC instead of a translated PC? Because the processor's working in virtual addresses. Okay? And so now we call the string length, and we're going to fetch from 360. Well, to get from memory, now we got to translate. So to translate to 360, again, we're going to look and we're going to find that that's in code 0. And so we're going to translate to physical for 360, getting this load instruction. Okay, it's loading a constant. And so then we're going to move 0 into V0. And why do we not translate 0? Because 0 is a constant. Okay, you don't translate constants. Okay? And then we're going to move PC plus 1, okay, or PC equals PC plus 4 into PC. Questions? Yes? So the question is it possible to have a stack span segments? So you, in principle, could, if you put the stack right on the edge, like you had a bunch of 1s up here, so that you'd roll over. You don't do that, though. It's just, that would be chaos, and nobody does. And in fact, once we have paging, we're not going to mess with that anyway. Any other questions? Should we finish this out? So notice, last but not least, we're going to fetch from 364, translate to 364. We're going to load a byte from A0. So now remember, A0 had this var x in it, but now because we're going to load a byte from there, we actually have to translate it because we're doing a data operation. So we're going to do a load byte. So at that point, we translate 4050. We have to write it all out. Look, that's 01 and a bunch of stuff. The top 2 bits are 01. So which segment are we in? Segment 1, which is the data segment. Well, that's good. Okay, I guess we didn't screw that up. Okay, and if we go to figure out where that is, it's in virtual segment 1. The offset is 50. Okay, take a look at this. 4050. If I chop off the 01 part, what's left over is the number 50. Okay, because I took the 01 off the top. And so when I basically, what's the base here? The base is 4800. I add the 50 to it, I get 4850, and I load the byte from physical address 4850 into T0, etc. Okay, this was probably painful enough to stop, but I will ask, are there any questions? Key things to get out of this slide are processor works in virtual space. So anything that has to do with addresses that are being manipulated or loaded into registers or moved in a way that isn't actually accessing memory, it's all in virtual space. It's only when you have to actually access, like load an instruction or load bytes, then you go through the MMU. Because that's the point at which virtual addresses are being put out there, okay? Now, observations about this are, 1, virtual address space has a lot of holes. So the segmentation is efficient for sparse address spaces. That's good. A correct program shouldn't really ever go into the gaps. If you try to go into a gap, then that'll cause a segmentation fault, at which point maybe you grow the size. When's it okay to address outside the valid range? Well, that might be how the stack and heap grow. We could be talking about that. We're going to make it much cleaner when we get to paging. You need a protection mode in the segmentation table. For instance, the code segment is typically read-only. So what you see here is I haven't actually shown you the notion that maybe code is marked as only allow reads, never writes. Okay, and the reason for that, there's many of them. One of them is a security reason, because if I allow my code to be written, then if somebody manages to do a Stack Overflow exploit or whatever, maybe they can overwrite my code. The other is if I'm sharing the code with two different processes, I don't want one of them to accidentally overwrite the code I'm executing. So typically code is marked read-only. Other things might be as well. Okay, so we don't have any way of dealing with that yet. What do you have to save and restore in a context switch? The whole set of segment registers. That's part of a context switch. Now, fortunately for you guys, you're dealing with an x86 style processor. When it context switches, part of the process saves the segment registers for you, so you don't have to do a lot of work there. If you were on something that actually didn't do that for you, then it could get a little complicated, but the kernel does that. Okay. What if not all the segments fit in memory? Well, an extreme form of... So, context switching, you imagine what happens is the timer goes off, you say this process is done for a while, let's swap out its segment registers, swap in some new ones, registers as well, and now we're running the next thread, okay, or the next process. We can keep doing that, and we get context switching, we get multiple processes running in multiple threads, just like you've been dealing with since the beginning of the term. But what if they don't all fit in memory because I've got so many processes running that I don't have enough physical memory? Now this gets kind of interesting. So in the case of segmentation only, we're going to fix this as soon as we talk about paging. There aren't a lot of good options here. Either a segment's entirely in memory or it's not, because there's no way to have part of a segment. It doesn't make any sense to talk about part of a segment being in physical memory. And so what we actually talk about in this is called swapping, where we actually take whole segments, swap them out for process one, and maybe swap something back in. So this is a whole new level of expense to context switching, because what it says is when I context switch process one, because I have not enough physical memory, I have to swap out all of process one or a lot of its segments and then swap in process two off disk. And remember, what's the number to remember for disk? How many instructions for a disk access? How many? 1 million. Yay, 1 million. Good, good, good. So, what might be a desirable alternative here? Some way to keep only active portions of a process in memory and the rest out on disk. Wouldn't it be great if we could divide things up into common sized, well, I hate to say it, pages, okay, which are all the same size so that I can swap out the ones I'm not using and only have the ones that I am using in memory. All right, and that's kind of our next topic. So the major problems with segmentation here is you got to fit variable sized chunks in memory. You may move the processes may need to be moved around because of fragmentation. There's limited options for swapping, and you got really bad fragmentation problems, in particular external fragmentation, which is where you have to fill the gaps between the chunks by moving, okay? All right, so that's good for now. We'll pick this up next time. But in conclusion, we talked a lot about segment mapping, so segment registers within the processor. Segment ID is associated with each access and often comes either from a portion of the virtual address or from the bits in the instruction. And every segment has a base and a limit of information. We're going to talk about next time page tables, where we start talking about general translation, where we can have fixed size pages, which are going to be 4K chunks typically. All right, you guys have a great weekend. We'll see you on Tuesday, assuming that we're still doing lectures, which I think we might be.
Is that a page size in the